So, hi and welcome everybody to the second part of Signal and System, part 2, which is related to Fourier transform. In the first part, we discussed Fourier series analysis. In this part, we will be concentrating mainly on Fourier transform. Some important Fourier transforms will be discussed. Also, some important Fourier transform theorems will be explained, and then convolution and modulation, and finally discuss and explain ideal filters. So Fourier transform definition. In Signal and System course, the Fourier transform and its inverse were defined by the following equation. Yes, you remember with me that this equation, nice equation we used to deal with. We used to tell you find G capital of JW in the frequency domain, and W in this case is equal to pi f, 2 pi f. Basically, you get this function g of t in time domain, and you multiply it by the exponential function e to minus jwt, and you integrate over t. And if I tell you find g of t, you just make this minus plus, and put this the frequency domain function inside the integration, and you get g of t in time. This is so in Signal and System, the term JW was used to make all transforms similar in form. Basically, we used it for Fourier, Laplace, DTFT, and Z transform. In this class, we used T pi f instead of W. We replace W by 2 pi f. So accordingly, we don't have JW, we have G of f, which is equal to the integration of G of t e to minus j 2 pi ft, integration over delta t. And if I ask you find G of t, you just, from minus becomes plus, and you put the frequency domain function here. The transform and its inverse are almost symmetric, only the sign in the complex exponential changes. Yes, symmetric, almost the same. This Fourier transform takes your signal from time to frequency. What's this? Inverse Fourier transform takes your signal from frequency to time. The result is time. This, since they are symmetric somehow, this will simplify a lot of the transforms and theorems. Clear? If g of t is absolutely integrable, you can integrate it and find a closed form for it, or the integration is less than infinity, it doesn't go to infinity, then g of f exists. So what's the difference between Fourier transform and Fourier series analysis that we discussed in the previous lesson? Fourier series analysis for periodic signal, Fourier transform for energy signals, for signals that are defined over a finite period and whose energy is finite. Yes, the energy of the signal is finite. How do you determine the energy and make sure that it's finite? You calculate this integration. Yes? This integration. If it is below infinity, then it's finite. If it is finite, then you have Fourier transform. Yes? You have Fourier transform. Yes or no? Yes. Then g of f exists for most frequencies f and has finite energy. If g of t is periodic and has a Fourier series, then g of f, if it is periodic and also has finite energy, g of f in this case can be written in this form. Summation of g and f naught, the frequency signals at fundamental frequencies in f naught, multiplied by delta f minus in f naught, which is the shift that can make. Basically, these are the basic things you need to know very basic ones, and then you move to practical implementation and how to calculate this and find this. For example, if I give you a signal g of t, which is exponentially decaying e to minus at, this is signal, but give me practical example that you can, where can you see this function? The channel. The wireless channel, when you transmit your signal from that tower to your phone, the channel basically, the first component that you receive from your transmitter has this amplitude, let's say this. The second one that gets reflected off that mountain, goes to the mountain, reflects and come to you, reaches you after some time, not, and with shorter amplitude. Why? Because it traveled more and get reflected off the mountain. And the signal that gets reflected off the bridge, for example, or off the car moving in the road, comes at a later time and the amplitude is even lower. So basically your signal was this, then this, then this, then zero. You don't get anything. This is e2 minus alpha t. This is exponentially decaying. Practical example, the channel that you receive at your phone. When your signal goes through the channel, the signal gets affected by this type of behavior. So the Fourier transform of one-sided decay, how do you find the Fourier transform? This is in time domain, but I want this in the frequency domain. Why would I need it in the frequency domain? Because there are times where mathematical calculation in time domain is so complex, so tedious, so sophisticated. To avoid that, we go to the frequency domain. In the frequency domain becomes much easier and simpler. That's why we care about Fourier transform. Now you understand the why. Once you understand the why, you really, really become able to link things with each other and think beyond what you read here. Now, how? How is really just practice. Why practice, and you know the basics in calculus, you can find it. Now I tell you how to find the Fourier transform. Fourier transform, I can find it by taking the integration of g of t multiplied by the exponential and integrate over delta t. How do you do that? Calculus 1. E to minus alpha t, e to minus j. If they have the same basis, you can sum them. So I get this function. Everybody with me, this becomes how? How? After you understand the why and the physical meaning, you move to how. Which is more important? The why, because the why makes you scientist. Think beyond what you have. How makes you implementer. Takes order and implement, just for the sake. So to be able to be good and successful in your field, you must know both. Most of the courses, they just focus on how to do that, and the questions also in the exam, how to derive this, how to find this, how to find the answer. But why? When you ask why, rarely you can find physically practical, convincing answers. So if you miss the why, you lose your motivation. You will always take the course and go out of the lecture and say, I don't know where the hell I will use this course. I don't know why I'm taking it in my degree. You understand me? But when you know the why, you start understanding where to apply this. How can I make use of this? How can I make money out of this? You know, the people who work on the stock market? Yes? The people who works on the stock market. Everybody knows the stock market? Like the dollar and lira, for example, or the gold. It's going like this, and all of a sudden goes like this, and then goes stable, and then all of a sudden goes like this. What's this? This is time series. Time series, they are related to Fourier series and to the signal and system things that I'm teaching you now. People, they hire engineers like you to be able to make them able to predict what will be the price after X time, after 10 days, or after 1 day, or 1 minute, or 1 hour. if you can predict what this will be, based on math, of course, and Fourier series analysis, and then they will pay you like per day $1 or $10,000 per day. If you can predict exactly for a company what will be this. So imagine, it's very valuable skill, extremely valuable. My students, one of them is working for a startup in Korea, I think. He's developing a machine learning algorithm, which is basically signal and system algorithm, but in machine learning context, to predict what would be the price of the stock after X days, X number of days, 10 days, 5 days. Practical implementation. So this means that the science you are learning here is useful, has practical applications, can make you money, can produce useful things to community. People will be careful about it. You understand me? So the time series here is somehow related to the things you are studying here. And then you find the answer. Once you find the answer, so the signal was time, real, now it's complex, J2 by F. If your signal is complex now, what do? You have magnitude and you have phase. How do you find the magnitude of this, magnitude of this, magnitude of this? You divide them over each other, you get the magnitude, you draw it. As a function of the frequency, frequency is continuous. And how do you find the phase? You get the phase of this, get the phase of this, tan inverse of the imaginary over the real, and you find the phase and you can draw the phase as function of the frequency. So you have two figures, one for amplitude and one for phase. Even though G of t is real, its transform is complex, as you can see here, it's complex. This is the usual situation, because you always have this J2 by F. So basically it reflects in the integration. We can rationalize G of F, yes? For example, what he's doing stupid things here. Let's see why. We want to draw the magnitude and Fourier and phase, yes? So here you multiply in this equation, we multiplied the denominator by A minus G2 by F, so that you get everything square, and here you divide it into two components, A over this minus J2 by F over this, and then you can take the magnitude of G of F and then the phase of G of F. The magnitude is this function and the phase is this function. Everybody with me? Everybody with me? Yes, the magnitude is this and the phase is this. Draw the magnitude. This is time, yes? This is the signal in time, the decaying G of t. The magnitude of it in the frequency is this, which is this function. And the phase, this one, tan inverse of this component over this component is basically this one, this function. So this goes to here. You care about the magnitude and phase, you draw them. This is how it was in time, this is what it's in frequency after you take it. So basically now with the computerization and MATLAB and many useful and handy softwares, you can do all these things automatically. You just input them, the function, calculates the integration, gives you the amplitude, the frequency, the phase, and you can draw them with simple command and see these functions. As if you have time at home, just try to do this in MATLAB and see how easy it is to be done. Just go here, come here and define G of t e to minus a of t. Find its Fourier transform, this integration using MATLAB, and then come here and draw its amplitude and phase. It's less than 5 minutes work. That can take from you maybe 20 minutes, 15 minutes, or 10 to 15 minutes from the function to the drawing. In MATLAB, you can do it in less than 1 minute if you are expert. If you are not expert like you can make it in 5 minutes. You can do it at home. Yes, let me know next lecture if you have done it or not. Okay. This MATLAB, take the Fourier transform, and I want you to be able to see these ones in MATLAB. See these ones. I'm not asking you to submit me anything because as we agreed, there is no homeworks, no assignments, no. It's just for you to learn and see how easy it is to be implemented in MATLAB. And if you have any problem in it, come to my office, I will show you. I will show you if you come and ask about it. Okay? Just to show you how simple and easy it is. So your friends who don't MATLAB, they struggle half an hour, 1 hour, and some functions they don't know how to find, and you are happy. You just enter the function, do some simple comments, and you get that drawing. So you are quick. You know how to use simulation. You know how to use softwares. You know how to... That's the power. You must be able to make use of the available technology. If you don't make use of technology, you are left behind. Everybody will be much better and faster than you. Yes? Why Germany and Europe became in the 90s, 19th century better than the other countries? Because they invented the printer. People keep writing and copying and this and that, and they can copy hundreds of books in just 1 day, and the others need years. So whoever makes use of technology first can make an impact to the world. Yes, isn't it? And this is similar, using software or keep using your hand to calculate. Yes, I know how to use it. I know what's the rules. But now, then what? Fast. Do it fast. Do it quickly. We can show you in next lecture maybe also how to do that, because I don't have MATLAB on this PC, but I have it in the other one. So other example. Now you are good with this example. Yes, you know how to do it by math. You know how to do it by MATLAB. You will go and do it by MATLAB. If you don't know, you can ask me, and this will be super easy for you. And now Fourier transform at frequency equals 0. If you calculate it, you take g of 0 and you substitute 0, and you take the integration of g of t. So now we come to the fact that g of 0 is the area under gt. G of 0, the frequency here, when I tell you g of 0, this is just to show you that when you find the integration at frequency equals 0, it's basically the integration of the original function. The integration of the original function is the area. Yes, integration is basically the area under that function. And this is called the DC value. For g of t equal e to minus alpha t u of t, g of 0, 1 over alpha is the only real value. It's also largest in magnitude. So here basically we are, for different values, for different cases, finding what's gf. What's the Fourier transform? What's the Fourier transform of minus f? The Fourier transform of minus f is equal to Fourier transform of the conjugate. So you find what's gf, and then you find the conjugate. What's conjugate? If you have minus j, put it plus. If you have plus j, make it minus. That's it. So conjugate here, it proves that how it is equal to j minus f. When you put the conjugate of the transform, it becomes the conjugate of the individual functions, and you take the Fourier transform of it, and it becomes g of minus f. Because when you take the conjugate of this, what happens here becomes plus. The minus becomes plus, as I told you. So as if you are taking the g of minus f. Duality, Fourier inversion theorem. If g of t has Fourier transform g of f, then g of f is equal to the Fourier transform of g of t e to minus j 2 pi ft delta t, and g of t is basically the inverse of this. You just remove the minus from here. Here g of t time, here frequency, and here there is no minus. This is inverse. Inverse transform differs from forward transform only in sign of exponent. Suppose we consider g of anything to be a function of t instead of f. If we apply the Fourier transform again, then you have g of t e to minus j2 by ft equal to the integration of g capital T e to minus j2 by f, but minus multiplied by t. So basically here we show you the duality. You have g of f here. What if instead of f you have t? It's also applicable, fine, go with it. It becomes now time frequency and frequency time. You exchange the variable. But math doesn't distinguish whether it's time or frequency. Math remains applicable. We can summarize this as the Fourier transform of g of t. If you have a signal in time domain, what's the Fourier transform? G of f. If you have g capital of t and you find the Fourier transform, what's in time? What's in the other domain? G of minus f. That's the difference. We call this principle the duality principle. So exchanging the variables adds a sign to the function in the other domain. Important Fourier transform, the unit rectangular function, rect. If you have rect, in the previous lecture we took the Fourier series analysis of rect. If you have rect, you can find the Fourier transform. How do you find it? What's the value here? 1 e to minus I2 by ft rect, and you find that it's sinc. But what's the difference here? Sinc over continuous frequencies because it's Fourier transform. But here that was Fourier analysis at certain coefficients, at certain points. By duality, we know that Fourier transform of sinc is equal to rect minus f, and it's equal to rect f. Why? Because rect is even function. Yes? It's the side here is similar to the side on the other area. Every finite width pulse has a transform with unbounded frequencies. What does this mean? Yes? If you have every finite width pulse, this is pulse, finite width. The transform has unbounded frequency, means this. Goes to infinity, from infinity to infinity. Why? Because this edge, it's impractical to design it in practice. Anything that you confine it in one domain, in the other domain, it's not bounded. Physics. If you remember in physics, if you have taken the quantum physics, they say if you can measure it in time precisely, you cannot measure it precisely in the frequency. It's the same in signals here. If you bound something precisely in one domain, in the other domain, it's not bounded. Clear? If alpha greater than 0 and g of t is a signal with Fourier transform g of f, then Fourier transform of g alpha t is basically when you multiply your time domain by alpha factor and alpha greater than 0, as if you are dividing the frequency by alpha. We call it time scaling. So when you make time scaling in the frequency, you shrink it because you divide by alpha now. If alpha less than 0, change of variable requires reversing limits of integration. So it becomes just minus if it is less than 0. Combining both cases, Fourier transform of g alpha t is equal to 1 over magnitude of alpha g of f minus alpha. So basically if alpha, now we understand if alpha greater than 0 or less than 0, there is a difference in minus. But what if alpha between 0 and 1? What happens? If it is half, for example, what happens to the frequency? It becomes like 2f. So instead of reducing the frequency, you are making the frequencies larger. So it becomes like if it is between 0 and 1, what happens? for example, half becomes 2f, so your signal shrinks or expands, basically shrinks. But if it is, if alpha greater than 1, let's say f over 5, expands. So it's compressing in time corresponding to expansion of frequencies. This is what you want to know. If you compress your signal in time, compress it, you expand it in frequency. It expands automatically. If you compress it in frequency, it expands in time. So this is the relationship between them. The sharper the pulse, the wider the spectrum. Time scaling example. This is an example, you can have a look at it at home. Important Fourier transform, shifted impulse. If you shift by t naught, you just multiply by e2 minus j2 by f, t naught. And these are examples, we can have a look at them in the next lecture. So basically we stop here, and next lecture we continue from this slide. Thank you very much, and continue next lecture inshallah.